Everyone is telling you AI will replace engineers. The 72 hours before a 3-nanometer tape-out tell the opposite story. A tape-out is the moment a chip design, billions of transistors, 2 years of work, more than $20 million of mask cost, finally leaves the design team and goes to TSMC's fab in Hsinchu. There is no rollback. There is no software patch. Whatever ships in that GDS file is what comes back from Taiwan 90 days later as silicon, for better and very often for worse. And in the 72 hours before that file goes, the most expensive technical decisions in the entire program are made. Not by a place and route tool, not by a synthesis engine, not by an AI copilot, by a human sitting in front of 3 monitors, drinking the 4th coffee of the day, making calls that move millions of dollars per hour. This video is about what those 3 days actually look like, why every major attempt to automate them has stalled, and which company in the entire semiconductor stack profits the most from the fact that they cannot be automated. The answer at the end is not the engineer. The cast of a modern tape-out is not one engineer. It is roughly 100, distributed across functions that did not even exist as separate roles 20 years ago. Design verification, design for test, analog, mixed signal, package, layout, security, and on the largest programs, machine learning. But at the center of the final 72 hours sits the physical design engineer, the PD engineer. The PD engineer is the person who turns a logic netlist, the abstract description of what the chip should compute, into a real geometric layout that respects every physical rule TSMC enforces at 3 nanometers. Power, timing, signal integrity, manufacturability, yield. They are the integrator, the one role that has to hold every other team's constraint in mind simultaneously. And in the last 3 days before tape-out, 4 hard windows show up on the schedule, set by the program manager months in advance, non-negotiable. T-minus 72 hours, final timing closure. T-minus 48, power and IR drop sign-off. T-minus 24, DRC and LVS clean. T0, GDS handoff to the foundry. Each window has a thing AI tools can do today and a thing only a human can decide. Walk through them in chronological order, and the line between automation and judgment becomes very clear. That line is also the line that decides which jobs in the chip industry survive the next decade, and which ones get absorbed into the EDA tools. 72 hours out, the static timing analysis report comes in. On a 3-nanometer system on chip, that report is tens of thousands of pages. Every register-to-register path in every clock domain, across every process, voltage, and temperature corner. The summary line is what matters. 200 paths failing. The PD engineer's job is not to look at all 200. It is to look at the slowest 5, decide which are real, and decide what to do about them. Some of those paths are in standard cells, the synthesis tool already optimized hard. There is no more room to shrink the gate. Some are bus paths from one corner of the die to the other. A routing problem, fixable by a metal-only engineering change order. But that ECO will reshape 5 other paths. Some are false paths from a clock domain crossing that the timing tool flagged because the constraints file is wrong. Synopsys DSO.AI and Cadence Cerebrus, the modern AI-assisted place and route tools, can identify all 3 categories. They are very good at it. What they cannot do is decide which violation to accept under a sign-off waiver, because the customer ships in 3 weeks and the path is on a debug-only diagnostic register that never runs in mission mode. That decision involves the customer's contract, the program manager's risk tolerance, and the experience of having seen similar waivers go wrong on previous projects. It is a business call wearing a technical disguise. A human PD engineer makes it and signs their name on the waiver document, which will sit in the program audit trail for the next 10 years. 48 hours out, attention shifts to power. The IR drop simulation runs across the full power grid. Every metal layer, every via, every decoupling capacitor on the die. The output is a heat map. Red zones mean the local voltage at a transistor sags below specification during peak switching. On a 3-nanometer die packed with high toggle compute blocks, a neural processing unit, a GPU core, a matrix multiply engine, red zones are not rare, they are the norm. The PD engineer reads the map. The fix is never a single move. Add a decoupling capacitor, fill near the hotspot, and there is less area for logic. The chip just grew, and the cost per die just went up. Widen the power straps, and there is less routing room. Yesterday's timing closure breaks. Increase the on-die voltage regulator headroom, and the package thermal budget changes. The package team needs to be told, and they will not be happy. Every fix moves a different number on a different team's spreadsheet. The AI tool runs the simulation in minutes. It even suggests fixes ranked by predicted improvement. But it does not know that this specific chip is going into a flagship phone where the customer has already committed to a 30mm square package, or that the program's thermal budget was set 18 months ago in a system architecture review the PD engineer attended in person. The integrator role, holding the package, the board, the use case, and the customer contract in working memory at the same time, is what makes the fix the right one, or, when it goes wrong, the wrong one. 24 hours out, the design hits the foundry sign-off deck. For TSMC's 3-nanometer process, that deck contains design rules that fill thousands of pages. Pitch rules, density rules, antenna rules, dummy fill rules, end-of-line spacing, color rules for the multi-patterning layers. The full check runs overnight on a few hundred CPUs. 500 violations come back. The PD engineer triages. The first 450 are mechanical. Auto-fill density too low in this corner. A missing dummy via in that channel. An antenna ratio just over the limit on a long net. The tools fix those automatically by morning. The last 50 are the ones the tools flag but refuse to touch. An antenna violation near a high-impedance analog input. Fixing it adds a diode that perturbs the analog, matching the mixed signal team spent 6 months tuning. A density rule next to an embedded memory macro. The memory vendor's hard macro is in violation, and only the vendor can sign off on changing it, which takes a week. A polysilicon pitch exception on a custom standard cell the design team made for a Cerebrus. The foundry's deck flags it because the deck does not know about the custom cell, and the answer is to file a waiver document with TSMC's process engineering team. Each of these decisions has 3 options: fix it in-house, negotiate a waiver, get the third-party vendor involved. Each option has a time cost, a risk cost, and a relationship cost with TSMC, because every waiver burns a small amount of trust that the next program will need to draw on. The AI tool does not weigh relationships. The PD engineer does. The final 6 hours are not technical. They are organizational. Static timing analysis has signed across every PVT corner. IR drop is green. DRC and LVS are clean. The design verification team's last regression hit 100% functional coverage. The design for test team has scanned every flip-flop and committed to a target test cost. The package team has finalized the bump map and the substrate. The mixed signal team has signed off on every analog block. The PD engineer collects every email. There is a meeting, sometimes physical, more often a chain of acknowledgments over the corporate messaging system, where each function owner says, on the record, that their piece is ready. Then the PD engineer commits the GDS to the foundry handoff server. Once that file goes, $20 million of mask cost, typically 40 masks for a 3-nanometer node, each one $500,000, is in motion at TSMC. 90 days from now, silicon comes back. If the chip is broken on first silicon, the first rest spin costs another mask set and another quarter of the program calendar. The second rest spin can cost the program entirely. Customers move on, the market window closes, the design team's roadmap slips a year. There is no AI in the room making the commit call. There is one named human accepting the financial and legal accountability that the corporate structure requires to exist. The sign-off email is the artifact that internal auditors, the customer's procurement team, and, if something goes wrong, eventually a court will read. That artifact has to have a person's name on it. Not a model's name, a person's name. So why does the 72-hour window stay human when so much of the design flow before it has been automated? 3 reasons. Reason 1, million-dollar decisions per hour, a timing waiver, a power trade-off, a DRC exception. Each one moves a number on a budget the AI tool does not see. The PD engineer is making business calls wearing technical clothes, and the business does not trust a model to sign that big a number. Not in 2027, probably not in 2030. Reason 2, cross-domain context. The PD engineer holds the package model, the board model, the foundry rules, the customer's product roadmap, and the program's deadline and working memory at the same time. No single AI tool today has access to all 5. The EDA tool sees the netlist. The power tool sees the grid. The DRC deck sees the geometry. None of them see the customer contract. Reason 3, accountability infrastructure. Sign-off is not a technical artifact. It is a legal artifact. The corporate finance system, the customer's quality assurance audit, and the foundry's mask order all require a human signature. Not because the technical case demands it, but because the liability case does. Until product liability law evolves to accept signed model output as binding, and that is a decade-long change, not a tool change, the human stays. The non-obvious winner here is not the engineer. The engineer is tired, underpaid for the responsibility, and looking at a market where headcount is flat. The real winners are Synopsys and Cadence. The 2 EDA companies sell the AI augmentation that makes the engineer faster, and they sell the seat license the engineer needs to do the job at all. AI does not disintermediate the EDA duopoly. It lets them raise prices on both sides. That is one day in the life of one role in the chip industry. There are dozens more. Design verification engineers running billions of simulation cycles. Design for test engineers compressing test data so a chip can be screened on a tester in under a second. Package engineers solving thermal puzzles that decide whether a phone melts in summer. Real Silicon Jobs is the new series. Subscribe to see what the people who actually ship chips do before AI tries to convince you it can do their job. Next episode goes inside design verification. Watch the numbers.